Our galaxy, an enormous system of clouds of glowing gas and 100 billion stars, is also known as the Milky Way. Light takes 100,000 years to cross the galaxy from side to side, and the center lies in the constellation of Sagittarius, obscured from view by clouds of dusty gas that drift among the stars. Far from the galaxy's center is our star, the Sun, the disk and halo. The galaxy comprises two basic components, disk and halo. The Milky Way is our panoramic view of the disk with a diameter of about 100,000 light-years and a thickness of about 1/20th or less of the diameter. The disk is composed of stars and interstellar gas and contains over half the galaxy's visible mass. The gas amounts to 1/10 of the matter in the disk, and the dust amounts to about 1% or more of the mass of the gas. The stars, gas, and dust disks rotate like a giant carousel in the galaxy's center or nucleus. Most of the stars seen in the sky are in the disk and are separated from their nearest neighbors by distances of a few light years. The Sun is 30,000 light years from the nucleus. It moves 300 kilometers per second and takes 200 million years to travel around the galaxy in a circular orbit. In its lifetime, the Sun has journeyed 25 times around the galaxy. The spherical halo, centered on the nucleus of the galaxy, has a diameter of roughly 200,000 light-years. The central region of the halo forms the nuclear bulge of the disk. Outside the nuclear bulge, the halo consists of low-density gas, widely separated stars, and about 120 globular clusters. Globular clusters are compact systems of hundreds of thousands of stars, and each globular cluster moves in an elliptical orbit about the nucleus of the galaxy. The halo does not rotate with the disk. Two populations of stars. The flat disk, rich in gas and dust, rotates. The spherical halo, poor in gas and dust, rotates much slower. Walter Baade discovered a further distinction in 1942. A different kind of star populates each region. The two kinds of stars are known as populations 1 and 2. The disk contains mostly population 1 stars, and the halo contains mostly population 2 stars. Population 1 stars, the disk stars, are the kind we have considered. The Sun is a population I star. These stars are usually much younger than the galaxy and contain various chemical elements heavier than helium, whose total abundance by mass is 1 to 2%. Gas clouds in the disk give birth to new stars. At their death, many stars leave a legacy of heavy elements that have been ejected into space. Each newborn population of stars inherits heavy elements from stars previously dying. Over time, the reservoir of gas in the disk decreases, and its enrichment with heavy elements increases. In interstellar space, atoms of heavy elements collide, tend to stick together and form tiny dust-like grains. These dust grains are usually less than 1 micron, 1/10 of 1,000th of a centimeter, in size. Big enough, however, to absorb visible light. The tiny dust grains ride the atomic winds between the stars and collect in the dark clouds where new stars form. The halo contains population 2 stars, which are characterized by numerous globular clusters and nuclear bulges. The density of gas in the halo is much too low to form new stars, and most halo stars were born long ago when the galaxy was young. Their estimated ages lie between 8 and 15 billion years, and they formed from hydrogen and helium gas that contained almost no heavy elements. Planets cannot form from hydrogen and helium alone, and the halo stars seem unlikely to have planetary systems. In the younger population I stars, which formed from hydrogen and helium contaminated with heavy chemical elements. The heavy elements concentrated into dust grains. The dust aggregated into meteoroids, forming planets and the cores of large gaseous planets. Possibly, Most population I stars, at least those similar to the Sun, possess planets. And these are the places where extraterrestrial forms of life might exist. In the central region of the galaxy, the nuclear bulge, there is a mixture of disk, population 1, and halo, population 2 stars. Although it is convenient to think of two distinctly different populations, the young disk stars and the old halo stars, the first rich and the second poor in heavy elements, naturally, many intermediate populations also exist. Star clusters and their distances. Star clusters are of two types, open and globular. Open clusters in the disk are loose aggregations of young population I stars. These clusters usually consist of hundreds of stars and are often associated with gas clouds for a few million years, as seen in the Pleiades cluster. Globular clusters, found mostly in the halo and the nuclear bulge, are spherical. They have diameters of about 100 light-years and consist of hundreds of thousands of old population 2 stars. Clusters of both types, open and globular, are important because they enable the astronomer to estimate distances. The distance of a nearby star is found by parallax measurements. The distance of a star farther away is found by comparing its apparent brightness with the brightness of a similar nearby star at a known distance. Better results come from comparing clusters rather than single stars. All stars in a cluster have much the same age, a similar composition of chemical elements, and approximately the same distance. The cluster consists of stars of various brightnesses and surface temperatures, and we take its family portrait by constructing an HR diagram in which the apparent brightness of each star is plotted against its surface temperature. All stars fit beautifully on a well-defined main sequence. By comparing the family portraits, or HR diagrams, of different clusters, we find their relative distances. Thus, if the main sequence in one, the HR diagram is 4 times fainter than the main sequence in a second HR diagram, the first cluster is twice the distance of the second. This method works well, particularly when corrections allow for the difference in element composition of the clusters. The nearest open cluster is the Hyades. It outlines the face of the bull in the constellation Taurus and consists of at least 200 stars at 140 light-years distance. This important cluster is sufficiently close for its distance to be determined by parallax measurements. Also, its distance is determined by the moving cluster method. The Hyades cluster is moving away from us and appears to be shrinking slowly in size. By measuring its velocity from the Doppler effect and its apparent rate of shrinking, we can determine the distance of the Hyades cluster. From the known distance of the cluster, it is then possible, by main sequence fitting, to determine the distances of other open clusters that are farther away. A few open clusters at known distances contain Cepheid stars. These pulsating stars obey a period luminosity law. The pulsation period is related to luminosity. The Cepheids are about 10,000 times more luminous than the Sun, and can be observed at large distances. With the luminous Cepheids as yardsticks, we can now take giant strides and measure the distances of nearby galaxies. The Hyades cluster is thus very important. Its distance determines the size of our galaxy and other galaxies, and even the size of the universe. Clouds of gas and dust. The determination of astronomical distances faces many uncertainties, not the least of which is the correct allowance for starlight absorption by dust in interstellar space. The word nebula, cloud, was once used in astronomy to mean any fuzzy patch of light in the night sky. In the 18th century, Charles Messier catalogued many conspicuous nebulae, some of which, as we now know, are distant galaxies, such as the Andromeda Nebula. The word nebulae is now used primarily for interstellar gas clouds, and we distinguish between reflection nebulae and emission nebulae. Reflection nebulae reflect light from nearby stars and appear bluish in color. Emission nebulae, heated by nearby or embedded stars, emit their light and appear reddish. Many large and non-luminous clouds are widely distributed in the disk, obscuring more distant stars and galaxies from view. Early in the 20th century, astronomers suspected that starlight is absorbed by dark matter drifting in space between the stars. This obscuring medium was finally established in 1930 by Robert Trumpler of the Lick Observatory. We now know that the obscuration is caused by small grains of matter or dust distributed in the disk, particularly in gas clouds. Roughly 1 to 2% of the mass of interstellar matter is in the form of dust. Trumpler found that the intensity of starlight, owing to absorption, is halved every 3,000 light-years traveled in the disk. Thus, a disk star 6,000 light-years away has an apparent 1/4 of the brightness it would have in the absence of absorption. In the disk, stars are seen telescopically to distances of several thousand light-years. At greater distances, particularly in the direction of the galactic center, they become obscured from view. The dust acts like a layer of fog in the disk. Looking at the plane of the Milky Way, we see many nearby stars but no galaxies. Looking perpendicularly out of the plane of the Milky Way, we see few stars and many distant galaxies. This holds true in visible light, but not in infrared and radio signals that can penetrate the fog. Wavelengths larger than dust grains are difficult to absorb or scatter. This phenomenon explains why red light penetrates better than blue light in foggy weather. Long infrared and radio waves can reveal the inner region of the galaxy from view. Observations at these longer wavelengths reveal that the nuclear bulge, extending 10,000 light-years from the nucleus, is a complex system of swirling gas and multiple stars. Old and young stars are thickly distributed in this central region and are hundreds of times closer to one another than in our region of the galaxy. Several strong radiation sources exist in the nucleus's center, prompting astronomers to conjecture that the nucleus contains one or more massive black holes. These monsters of the deep cannot by themselves visibly radiate, but in falling gas, compressed and thereby heated, can radiate strongly. Spiral arms. The striking thing about many external galaxies is their spiral-like appearance. Studies of the distribution of gas and stars in the disk show that our galaxy also has a spiral structure. Spiral arms extend outward from the nuclear bulge, luminous with young stars and bright gas clouds. We see the spiral structure of external galaxies because their spiral arms contain bright stars and gas clouds. Other, less conspicuous stars in their disks are arranged more uniformly. At first, astronomers thought spiral arms always contained the same stars, and stars and spiral arms rotated together in the disk. But this idea contradicted appearances. The inner stars of the disk revolve about the galactic center more rapidly than the outer stars in the way that inner planets revolve about the sun more rapidly than outer planets. Therefore, the arms would slowly wind more and more and form a progressively tighter spiral. Each spiral arm would gain an additional turn every 100 or so million years. Yet many spiral galaxies, apparently billions of years old, have only 1 or 2 turns. This winding problem, as it was known, was solved by the Swedish astronomer Bertil Lindblad, who proposed a density wave theory. According to the density wave theory, spiral arms are ripples, or density waves, that travel around the disk like sound waves in the air. Each spiral arm is a spiral-shaped ripple that moves around in the disk and preserves its shape. Spiral arms are simply regions of higher gas density. The higher gas density triggers star formation, in a way not fully determined, and the spiral arms contain newborn stars. The gas and stars take millions of years to pass through a spiral arm. but the brightest stars have lifetimes of only a few million years, and by the time they move out of a spiral arm, they have died. A deficiency of bright stars and their associated luminous gas clouds exists between the spiral arms. Hence, spiral arms are conspicuous because they contain the brightest stars. The distribution of older stars in the disk is only slightly disturbed by the passing spiral ripple, and their aggregate light shows very little spiral appearance. The distant galaxies, once known as nebulae, are separated from one another by millions of light years. They stretch away in countless numbers, seemingly endlessly, each a magnificent celestial city of stars moving serenely in the depths of space. Many possess distinguishing features that enable astronomers to classify them as either ellipticals or spirals. Elliptical galaxies, called ellipticals, have an oval appearance. Some are spherical, but most look like oblate spheres. Their outer regions fade away and they lack clear boundaries. Many, particularly large ellipticals, have bright centers. They contain almost no gas and dust from which new stars can form and consist mainly of old population II stars. The ellipticals cover a wide range of masses and sizes, from dwarf galaxies not much larger than globular clusters, to rare giant galaxies such as M87, and even rarer supergiant galaxies that are hundreds of times more massive than our galaxy and have diameters as large as 500,000 light-years. Giant ellipticals, usually type E0, pronounced E0, which are spherical in appearance, have conspicuously bright nuclei, whereas dwarf ellipticals lack bright nuclei. The majority of galaxies, over 60%, are ellipticals, and the majority of the ellipticals are dwarf systems. Spiral galaxies, called spirals, like our galaxy, have disks containing population I stars and halos containing population II stars. The galaxy has conspicuous spiral arms coiled around the central nuclear bulges. Spirals divide into two distinct sequences: normal spirals, denoted by S, and barred spirals, denoted by SB. Normal spirals form a sequence of three types. The SA have large nuclear bulges and tightly wound arms. The SB have smaller nuclear bulges and less tightly wound arms. And the SC has the smallest nuclear bulges and the least tightly wound arms. Our galaxy and M31, Andromeda Nebula, are type SB. About 1/3 of all spirals are the barred type. They are classified as SBA, SBB, and SBC, according to the size of the nuclear bulge and tightness of the spiral arms, exactly as in normal spirals. A bright central bar, projecting beyond the nuclear bulge and connecting with the spiral arms, distinguishes them. This bar consists of stars and gas, but why it exists is not fully understood. Spirals are rich in gas that concentrates in their disks and feeds the birth of new stars. Unlike ellipticals, these galaxies have stars of all ages, with the young population of I stars in their disks, and the old population of the Chi stars in their halos and nuclear bulges. They do not exhibit the great range of masses and sizes of the ellipticals, and their masses usually lie between 10 and 1,000 billion solar masses. The majority of bright galaxies are spirals. Ellipticals, however, are the most numerous, and the brightest of all galaxies are the rare giant and even rarer supergiant ellipticals. Tuning fork diagram. Edwin Hubble at Mount Wilson Observatory arranged the galaxies in an orderly diagram resembling a tuning fork. Ellipticals form a sequence in one branch, arranged in order of increasing ellipticity, and normal and barred spirals form separate sequences in two parallel branches. The diagram classifies galaxies by their appearance. An E0 galaxy, for example, might be a spherical system or a flattened elliptical system seen face-on. At the junction of the three branches, Hubble placed the intriguing S0 galaxies that combine the properties of ellipticals and spirals. They are disc-shaped, like spirals, but lack gas and spiral structure, and therefore resemble. They, in fact, look just like spirals swept clean of gas and dust. The amount of interstellar gas in galaxies increases from left to right in the tuning fork diagram, from ellipticals to spirals. In ellipticals, the amount of gas is very small. It is also small in S0 galaxies, and progressively increases in the spirals as we go from SA and SBA to SC and SBC. The effect of rotation is more pronounced as we go from ellipticals to spirals. It was originally thought that galaxies evolved along the tuning fork diagram from left to right. That is why galaxies on the left are called early type, and those on the right are called late type. Then it was thought that they evolved from right to left. Astronomers now think that significant evolution along the tuning fork diagram is unlikely, and the basic properties distinguishing ellipticals and spirals were probably determined at the time of their birth. At least 1/10 of all galaxies have an irregular appearance and are classified as irregulars, denoted by R. Our nearest galactic neighbors, the Small and Large Magellanic Clouds, are examples of irregular galaxies. These galaxies have forms similar to those shown in Holton Arp's Atlas of Peculiar Galaxies. Their peculiar appearance often results from tidal interaction with adjacent galaxies. Clusters of galaxies. Galaxies are not uniformly distributed in space, but congregate in clusters of different sizes. The massive regular clusters of galaxies, looking like magnified globular clusters of stars, are spherical. Their galaxies concentrate in the central regions. They are rich, have a large membership, and contain thousands of galaxies, mostly elliptical and S0 types. Supergiant ellipticals, which have conceivably grown to their colossal size by swallowing smaller galaxies, often reside in the central regions. Regular clusters are typically 10 million light-years in diameter and lack sharp outer boundaries. They contain intergalactic gas and intergalactic stars and globular clusters, through which the galaxies rush at speeds often exceeding 1,000 kilometers per second. The wind of intergalactic gas streaming through these fast-moving galaxies is strong enough to strip away their interstellar gas. This suggests that S0 galaxies in the great clusters were once ordinary spirals, and their gas has been swept out by intergalactic winds. All other clusters of galaxies are irregular. They have various degrees of richness and are far more numerous than the rare regular clusters. They lack spherical symmetry and strong central condensation and contain a mixture of all types of galaxies. The great irregular clusters are clumpy and look like fused aggregations of smaller clusters. Irregular clusters range from rich aggregations of thousands of members, such as the Virgo cluster, to small groups of tens of members, such as our local group. Small irregular clusters, called groups, have typical sizes of 3 million light-years. Our galaxy is a member of the local group, a small irregular cluster of approximately 20 galaxies, and many more if we count midget systems that look little more than escaped globular clusters. Spread out in space, beyond the local, there are multitudes of other groups of galaxies. The nearest great cluster is the irregular Virgo cluster, at a distance of approximately 70 million light-years. The nearest regular cluster is the Coma cluster, at a distance of approximately 450 million light-years. Beyond about 100 million light-years, the galaxies appear to thin out slightly, and we now know that galaxies are grouped to form superclusters. The local supercluster we occupy has its center near the Virgo cluster, which is known as the Virgo supercluster. Distances of galaxies. Determining the distances to galaxies is extremely important in cosmology, but also extremely difficult. By measuring the apparent brightness of their most luminous stars, it is possible to determine the approximate distances of nearby galaxies. The bright Cepheids aid in charting the immediate extragalactic neighborhood. It is difficult to determine the distances of galaxies farther away, and the uncertainty increases with increasing distance. The apparent brightness of the most luminous stars and globular clusters is a distance indicator of up to about 80 million light-years. The apparent size of highly luminous clouds of gas and the brightness of supernovas take us farther out. Beyond 100 million light-years, all distances are uncertain by a factor of 2, perhaps even more. Galaxies themselves must now be used as distance indicators. What we see far out in space happened far back in time, when the galaxies were younger and not the same as now. And allowance for evolutionary changes adds to the many difficulties of determining the distances of very distant galaxies. Birth of galaxies. Most galaxies contain old population II stars and have ages of many billions of years. And most, if not all, were born long ago. Matter in intergalactic space is now too low in density to give birth to new galaxies. An average density of matter in a galaxy like ours is 1 hydrogen atom per cubic centimeter. This value would be the density if all stars were dissolved into gas and spread out in a sphere of diameter 100,000 light-years. Roughly, this is 1 million times greater than the average density of ordinary matter in the universe. The universe expanded and therefore was denser in the past, and the galaxies were crowded closer together. 5 billion years ago, when the solar system was born, the average density of the universe was roughly twice its present value. And 5 billion years earlier, still, the galaxies were only half their present average, separating distance. And the density of the universe was 8 times its present value. Much earlier, when the average density was greater than 1 million times its present value, galaxies did not exist, at least not in their present form, because they would be crushed. They come together beyond recognition in a universe denser than galaxies. The galaxies originated in rudimentary form when the expanding universe had an average density of less than 1 hydrogen atom per cubic centimeter. According to cosmological theory, the galaxies originated in an expanding universe over 100 million years. Proto-galaxies. Most theories on the origin of galaxies start with small variations of density in the very early universe. The density perturbations grow and eventually develop into proto-galaxies. Let P represent density, and 8P represent a small perturbation in density. Both P and 8P decrease with expansion in the early universe, but 8P decreases slower than P. Hence, the important ratio 8P equals P, known as the contrast density, steadily increases. Initially, the contrast density 8P equals PE is much smaller than 1 trillionth. But eventually, when 8P equals Pi has grown and attained a value near unity, we reach the formation stage of protogalaxies. Protogalaxies begin as large concentra, ions of hydrogen and helium gas. Helium was made from hydrogen in the early universe, with masses ranging from millions to trillions of solar masses. These cool gas concentrations, or globes, continued to expand more slowly than the universe, and their separations widened. At some stage, each globe ceases to expand and begins to collapse. A view of how these collapsing gas globes might have formed into galaxies is as follows. Collapse theory. We consider a possible picture of the formation of a giant galaxy. At first, a globe of gas has roughly uniform density. By the time a globe attains its maximum size of about 500,000 light-years in diameter, the density is no longer uniform. At about this time, the earliest population II stars begin to form in the central region, where the density is highest. The brightest of these first-generation stars evolve rapidly and erupt as supernovas, ejecting gas enriched with heavy chemical elements. Meanwhile, the whole globe of gas has begun to collapse freely under the influence of its gravity. The collapse lasts hundreds of millions or even billions of years. Stars continually form in the central region, and the brightest ones last only millions of years. Therefore, the protogalaxies in falling gas is steadily enriched with heavy elements. We must understand that stars, once formed, cease to participate in the general collapse of the protogalaxy. Each newborn star initially moves inward, but it follows an elliptical orbit after its formation, and its average distance from the center tends to stay constant. We have a picture of a collapsing protogalaxy, as proposed in 1962 by Olin Egan, Donald Lyndon Bell, and Alan Sandage, in which the central region becomes a swarm of population 2 stars. This swarm of stars is roughly spherical, and our galaxy has a diameter of about 100,000 light-years. Thus, the central region of the protogalaxy has become what would later be the galactic halo. Through the halo of stars falls the rest of the collapsing protogalaxy. This is the outside-in theory of galaxy formation. The inside of the protogalaxy forms the halo, then the outside of the protogalaxy falls in, and finally forms the nucleus and disk of the newborn galaxy. What galaxy is the infalling gas that determines whether the galaxy is a spiral galaxy or an elliptical galaxy? Let us consider a protogalactic globe of gas initially in uniform rotation. The outer parts have higher rotational velocities than the inner parts. As before, the core of the globe transforms into a swarm of stars, and because of the core's low rotational velocity, the swarm is almost spherical in shape. As the infalling gas from the outer regions falls inward, its rotational velocity increases like a ballet dancer rotates faster as she lowers her arms. The descending gas collects the previously expelled heavy elements and partially fuels the creation of new stars. These new stars are intermediate between population 1 and population 2 stars, and their distribution in space is less spherical than that of the first-generation stars. The surviving gas cannot fall to the center because of its rotation. Instead, it settles into a rotating gaseous disk of hydrogen, helium, and most heavy elements ejected from halo stars. Population Y stars now begin to form in the gaseous disk. But rotation and the presence of magnetic fields greatly impede star formation, and to this day, only a few stars are born each year. The original gigantic gas globe has collapsed, producing a spiral galaxy. Where does the initial rotation come from? We do not know for certain. Perhaps the globes of gas pull one another into rotation by their gravitational interactions, or the initial perturbations in the very early universe have rotation. Whatever the preferred theory, one concludes that some protogalaxies have more rotation than others. Let us then consider a globe of gas that has a rapid rotation. As before, the first-generation stars form in the central region, and the infalling gas of the outer regions is partly consumed by the formation of new stars. But the infalling gas now lacks sufficient rotation to create a large disk of swirling gas. Instead, the gas continues to fall and is continually consumed by star formation. The gas that survives converges on the center and settles in the nucleus. The original gas globe has finally collapsed and produced a large elliptical galaxy. The rotation was never sufficient to form a large gaseous disk, but was sufficient to produce the moderately flattened distribution of stars we see in many ellipticals. The initial rotation and the initial density in protogalaxies are important. The star formation rate depends on gas density. The higher the density, the faster stars form. If a protogalaxy has a higher density, because it separates at an earlier stage in the expanding universe, stars form more quickly, and no infalling gas survives to form a disk or a nucleus. This theory might explain how small ellipticals form. In small, low-mass galaxies, the ejected gas from firstborn stars never gets incorporated into later stars, because all stars form more or less simultaneously. Possibly the ejected gas lingers around and is later swept out by galactic winds. We can explain the origin of large-scale astronomical structures in one of three ways. The first is the fragmentation hypothesis, proposed by James Jeans, in which the universe first divides into large pieces, which then fragment successively into smaller and smaller pieces, ultimately terminating with stars. The second is the aggregation hypothesis, advocated by David Laser of Harvard University, in which the universe first divides into small pieces, which then cluster successively into larger and larger pieces, ultimately terminating with superclusters of galaxies. The third, probably closer to the truth, combines these two pictures. The universe first fragments into globes of gas, some of which may aggregate to form large protogalaxies and clusters of protogalaxies. The collapsing globes fragment into clusters of stars and then into isolated stars. The galaxies club together to form clusters of galaxies of different sizes, that in turn aggregate to form superclusters. The fragmentation and clustering processes thus appear to be of comparable importance in the structural makeup of the universe. Radio galaxies and quasars. In 1931, Carl Jansky of the Bell Telephone Laboratories detected radio signals from the Milky Way. This exciting discovery received wide publicity. Signals from Jansky's receiver were relayed and broadcast in a radio program in which the announcer said, "I want you to hear for yourself this radio hiss from the depths of the universe." In 1938, the radio engineer Grote Reber detected radio signals from the Milky Way and noticed that the signals were strongest from the galactic center and constellations such as Cygnus and Cassiopeia, radio galaxies. Hundreds of radio sources were discovered in the early years of radio astronomy after World War II, and the visible counterparts of many were identified by optical astronomers. Thus, Taurus A, the strongest of the observed radio sources in the constellation Taurus, was found to be the Crab Nebula, a chaotic cloud of gas produced by the supernova of 1054. Cygnus A, or 3C405, was identified as a disturbed-looking giant galaxy at a distance of 1 billion light-years. The most powerful of the optically identified radio sources were galaxies, and these radio galaxies, such as Cygnus A, emit millions of times more energy in radio waves than ordinary galaxies. Radio galaxies on photographic plates often have bright central regions and sometimes protruding jets, e.g., M87 and wispy extensions. The strongest radio galaxies radiate more energy in radio waves than visible light, and are usually giant ellipticals in rich clusters of galaxies. Radio waves from these sources are emitted by fast electrons moving in helical orbits in magnetic fields. The waves are known as synchrotron radiation because they are produced in high-energy synchrotron accelerators. Radio galaxies generate hordes of energetic electrons dispersed throughout their radio-emitting regions in a way not completely understood. Great strides have been made in radio astronomy, and it is now possible to study the structure of radio sources in detail. Most sources have a double structure. These sources emit radio waves from extended components lying on opposite sides of the source. The two components, or jets, extend to distances of hundreds of thousands, sometimes millions, of light-years. The energy radiated by the jets originates in the galaxy, presumably from its nucleus. Often a radio galaxy's central region, or nucleus, is a powerful radio emitter containing two radio-emitting components separated by distances of only hundreds of light-years. Thus, there are two varieties of radio sources: extended and compact sources, and some, for example Cygnus A, are both extended and compact. Martin Rees of Cambridge University has suggested that the combined output in waves and energetic particles from hundreds of thousands of pulsars in a galactic nucleus is beamed away in two opposite directions. The energy in these intense beams is then distributed over large regions that radiate radio waves. According to another idea, suggested by Soviet astronomers and Philip Morrison of Massachusetts Institute of Technology, the gas in the nucleus of a galaxy contracts and forms one or more supermassive stars that rotate and have strong magnetic fields. These spinars are millions of times more massive than the Sun and behave like titanic pulsars, radiating intense beams into intergalactic space. Developments in other fields of astronomy soon overtook these early ideas. Quasars. By 1960, radio astronomers had found and catalogued hundreds of radio galaxies, about 50 of which had been identified by optical astronomers as giant ellipticals. The unidentified radio galaxies seem much too faint to be recorded on photographic plates. Then, a sequence of events occurred in 1960 that led to the discovery of some very puzzling objects. The quasi-stellar objects, QSOs, later known as quasars. It was noticed that the radio source 3C48 is star-like in appearance, not nebulous like a galaxy, and emits strong ultraviolet radiation. Other objects of similar appearance, such as 3C273, were soon found. They were an unusual star in our galaxy that, unlike ordinary stars, emitted strong radio waves. In 1963 came startling news. Martin Schmidt of Mount Wilson Observatory had discovered emission lines in the spectrum of 3C273 that were shifted by 16% to longer wavelengths. In other words, the radio source had a redshift of 0.16 and receded from us at about 0.16, the speed of light. In an expanding universe, all extragalactic objects at great distances are receding from us, and as a result, the light we receive from these objects is redshifted. This is a subject to be discussed later, and here we need only remark that a redshift of 0.16 corresponds to a distance of roughly 3 billion light-years. The simple and logical explanation of 3C273 is that it is extragalactic, and its redshift results from the universe's expansion. Numerous other radio sources were optically identified as star-like objects with large redshifts, and it became evident that these star-like radio sources were remote beacons radiating enormous quantities of energy. Alan Sandage then discovered that many extragalactic star-like objects are radio-quiet. The word quasar, coined by the astronomer Hong-Yi Choi at the State University of New York at Stony Brook, is a contraction of quasi-stellar and is now used to denote all star-like objects of large redshift, whether or not they emit radio waves. The nearest quasar so far discovered is 3C273. Most quasars lie at distances of billions of light-years, and the most distant have redshifts greater than 5. A redshift Z means the universe has expanded one Z-fold since the emission of the light now seen. Thus, Z equals 1 means a 2-fold expansion. It is estimated that tens of millions of quasars are observable with the largest optical telescopes. When we look out into space to such large distances, we also look back billions of years into the past. We look back in time and see that quasars were far more numerous in the universe in the past than at present. They were sufficiently numerous when the solar system formed that at least one was near enough to be seen by the naked eye, gleaming in the sky like a brilliant jewel. Earlier still, shortly after the birth of galaxies, when the universe was 1/10 its present age, the quasars were all around, millions of times more numerous than now. The quasar puzzle. Quasars radiate energy at approximately 100 times the rate of all the stars in a giant galaxy. They squander energy at this rate for typically 1 billion or more years. If matter were annihilated and converted entirely into energy, energy equals mass times the square of the speed of light, some quasars would consume the mass of more than 100 million stars in their lifetime. The light from some quasars fluctuates in brightness, changing on timescales as short as weeks and even days. Normally, a luminous source cannot significantly change its visible appearance in a shorter time than it takes for light to travel across its size. When an object abruptly increases its light output, an observer sees a slower increase because light emitted from the nearest parts of its surface arrives first, and light from its more distant parts arrives later. Thus, if light varies in brightness in, say, 1 day, A spherical source has a radius smaller than one light day and is therefore smaller than the solar system. Imagine that a large ballroom represents the size of the galaxy. On that galaxy, a highly luminous quasar is no more than a speck of dust floating in the air. Quasars are powerful radio, infrared, visible, and ultraviolet radiation sources, and extraordinarily compact by astronomical standards. What are they? Active galactic nuclei. Radio quasars are similar to radio galaxies. Both have extended or compact radio-emitting regions. Radio astronomers cannot tell the difference. Also, optical astronomers cannot tell the difference between quasars and the bright nuclei of radio galaxies. Both appear to be the same. The nuclei of most giant ellipticals may pass through a quasar state in their early evolution, and most quasars pass through an active radio-emitting phase in their lifetime. Some giant spirals, known as Seyfert galaxies, have bright active nuclei that exhibit violent activity and resemble miniature quasars. Years have passed since the discovery of quasars, and many puzzles remain unsolved concerning how these compact objects generate and emit immense quantities of energy over a wide range of wavelengths. In the excitement that followed their discovery, several theories were proposed, such as the annihilation of matter and antimatter, dense stellar systems in which stars continually collide cataclysmically, dense stellar systems in which supernovas occur frequently, and even alterations in the known laws of nature. However, it is generally agreed that the radiation is fueled by the release of gravitational energy. Probably the mechanism begins with the formation of numerous stars in the nucleus, many of which evolve and become neutron stars and black holes. These compact bodies then accrete gas and release energy. There seems little doubt that stars more massive than the Sun, must collapse at the end of their evolution and become black holes. As we understand them, the laws of nature lead to this conclusion. Edwin Salpeter of Cornell University proposed the most successful and widely accepted explanation of quasars. The idea is that quasars are supermassive black holes that accrete gas. The theory has been broadened to include all highly agitated galactic nuclei, quasars, radio sources, Seyfert galaxies, and other similar strange objects, under the generic name active galactic nuclei. Supermassive black holes. Not all infalling gas is consumed in the birth of stars during the formation of a galaxy. The surviving gas finishes in either the disks of spirals or the nuclei of ellipticals. In a giant elliptical galaxy, infalling gas accumulates in the nucleus, possibly 1/10 the galaxy's total mass. Slow subsequent contraction of this matter reservoir creates a quasar that shines for the next billion years. In a giant spiral, however, the gas accumulating in the nucleus is much less, and nuclear activity is scaled down. The first step is likely forming numerous stars in a gas-rich nucleus, many of which rapidly evolve and become black holes. Imagine a black hole, initially a few times the mass of the Sun with a diameter of about 10 kilometers, located in a nucleus where gas is dense and millions of stars are huddled close together. The situation conjures up those terrible words, "Cry havoc, and let slip the dogs of war." The cry, havoc, was a command to massacre all without quarter. In the reign of Richard II of England, the cry was forbidden on pain of death. Gas swirls toward the black hole, forming an accretion disk where matter spirals in on the black hole. Incautious stars that wander too close either collide with one another or are torn to shreds by tidal forces, and their gaseous wreckage adds to the headlong rush that spirals in on the black hole. Next time you pull the plug out of a bath and see the water draining away in a dark vortex, think of a voracious black hole. The black hole rapidly grows in mass and occasionally swallows other lesser black holes. Provided the galactic nucleus is sufficiently rich in gas and stars, a black hole will grow in mass to 100 million times that of the Sun in a few hundred million years. and attain a size of 1 light-hour. A torrent of energy is released from the inflowing, swirling gas during its growth. As the gas swirls into the black hole, it compresses and heats to a high temperature, and energy is radiated away. A fraction, a tenth or more, of the mass of the captured gas is converted directly into escaping radiant energy. A monster black hole grows by accretion to 1 billion solar masses and radiates a total energy equivalent to at least 100 million solar masses. This picture of a quasar accounts for its brilliance and smallness, and might even explain how it became a radio source. The hot and therefore electrically conducting gas that swirls inward on the black hole acts as a vast electrical dynamo that generates oppositely directed beams of high-energy particles. These particles travel out and energize the radio-emitting regions of radio sources. According to this broad-brush picture, quasars exist in galactic nuclei in highly active states, and die only when most matter in the galactic nuclei has been swallowed or ejected from the nucleus. Thereafter, the black hole lies dormant, erupting sporadically whenever fresh gas supplies come. The gas concentration in the spiral's nuclei is less, and black holes in spirals are probably smaller than in giant ellipticals. Radio studies have indicated that the nucleus of our galaxy is this galaxy. Black holes might lurk in the nucleus and in the nuclei of